when you get to those numbers, when you're talking about trillions and billions and all those zeros, my brain just goes numb. There's this lack of comprehension that I'm well aware of. Like those numbers get thrown about, I go, oh, 200 billion.
No,
And it's just...
I think everybody does. I think every scientist, no scientist can picture that number. I mean, even the small number, 200 billion, which is the number of stars in one galaxy. And then when you say 2 trillion galaxies, that's, I challenge anyone to be able to picture that. But it is the reality that we've observed. We haven't counted all 2 trillion, by the way. We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed, and you know how many galaxies you've counted, and then you can spread that across the wider universe, and you get this picture of a vast and possibly infinite universe. I mean, we know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. And then that goes to your, can you picture infinity? Well, no one can picture infinity. There's a weird thing as well about, we say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. And then you can run time backwards, if you like, to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. And when I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. And the idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work. What terrifies you the most, an eternal universe or a finite universe?
Yeah, they're both incomprehensible. The eternal universe, if there was an eternal universe, does that negate the theory of the Big Bang, or does it mean that there's a constant cycle of Big Bangs and then expansion and then recompression? Or
yeah, it could do. So those theories are back in vogue. Some of those theories are back in vogue again. So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again. Or some of the other theories, there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, for why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And there was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed. And the just little patches stop, and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse. And we are in one of those bubbles. And that's one of the more popular theories.
There's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, little. They're a few times the mass of the sun. And they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun. But they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right? Essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. but they collapse to such an extent that there's a region around it from which light can't escape, and so nothing can escape, and that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon, and if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun...
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know, then there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses. And that's when you get a black hole.
We try to put that into perspective. The sun is 1,000,000 times bigger than the Earth.
Yeah.
And this neutron star is, would you say, 1.5 times the mass of the sun, but 10 miles wide?
Yeah. So, and there's loads of those around. They're called pulsars. So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was Little Green Men. So they called it kind of jokingly Little Green Men 1. And so, yeah, we've seen there's one called the Crab pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
Wasn't there some speculation that our solar system at one point was a binary star system, and that one of those stars had become a dwarf?
I don't know.
Someone had read something about that in relationship to the dense object they believe is outside the Kuiper Belt.
Yeah, I mean, there's some evidence. There's a bit of evidence that there's something out there.
Yeah.
Because of the periodic extinctions and things on Earth, like you get periodic bombardments from out in the Kuiper Belt. So yeah, I think one of the theories is
periodic extinctions.
Well, yeah. So for example, like there have been mass extinctions on Earth when a lot of the life died, and we don't know what caused all those, but sometimes they're impacts from space. That seems clear. And so, yeah, there are theories that there's something orbiting out there which can disrupt all these objects out in the Kuiper Belt that sends loads of comets and asteroids inwards to the inner solar system and can cause havoc. And so there's some people look at those theories. Then you can have the film about something else.
Yes.
because it's not really
Yes.
about that.
Well, did you like Event Horizon?
Yeah, I did actually. I thought that
It's
was
fun,
quite
right?
a cool film. Yeah,
Ridiculous.
I haven't
but,
seen it for
but fun.
years.
I always wanted to ask about their concept of propulsion. That almost like space would be flat, you would fold space over, and you would intersect those 2 points, and you would be able to travel vast distances instantaneously. Right? I'm doing a terrible job of explaining it, I'm sure, but is that a concept that people have actually considered?
Yeah, you can in general relativity. So Einstein's, I should say what it is. Einstein's theory of general relativity is our best theory of space and time, and so it really is, as we talked about before. It's you imagine space and time as a sheet. Just imagine it as a thing, sort of literally a sheet, a surface. And all the theory says is that if you put matter and or energy into that, then it curves it and distorts it, and it can stretch it and make it shrink. And so it's the response of space and time to matter and energy. So the simplest version would be the sun. So you put a big spherical ball of stuff in there, and it warps space and time such that the nice straight lines, something just travelling, minding its own business through that warp space, turns into an orbit.
And that's why you can actually kind of see things that are behind the sun?
Yeah.
Okay.
So light bends around the sun because it's just travelling through the curved space. The Earth goes round the sun because it's just rolling, minding its own business through the curved space. So an example would be, you might say, well, how does curved space, can that give rise to something that looks like a force, which is gravity? So the best analogy I know of is to think of walking around on the surface of the Earth. So if you stand on the equator of the Earth and you with your friend and you say, we're going to walk due north. So we're going to set off, let's say we're 1,000 miles apart on the equator and we're going to walk due north. What's going to happen? So you walk in straight lines. You don't change direction. You don't do any accelerating. But the straight lines are the lines of longitude on the surface of the Earth. So as you go further and further north, you get closer and closer together. And if you carry on to the pole, you bump into each other. But nothing's happened. Right? There's no forces acting. It's just that you're moving on a curved surface. And so you get closer. And that's basically Einstein's theory of general relativity. Now, why did I start talking about that?
Event horizon, the idea of folding.
Oh, yeah. So all you have to do to those folded kind of geometries is you have to try and specify where you would put the matter and what kind of stuff you'd put there to make the geometry fold in that way. And you can do it. So you can write down that geometry. So it's called a warp drive geometry, I think it's called. It's in textbooks. So you can do that to have a warp drive. The question becomes, what sort of stuff would you have to actually put into the real universe to make it warp in that way? And it usually turns out that it's the kind of stuff that doesn't exist, right? But it has properties. It's sort of matter or sort of energy that has properties that do not exist in nature as far as we can tell. But you can still write the geometry down in Einstein's theory.
So if you had the significant force or mass or whatever it is, if you had that stuff that doesn't exist, it is a concept that
so the geometry exists. So you can do it, and you can do the calculations, and you can see the warp drive. You can construct wormholes that connect distant regions of the universe, which you could use as time machines. You can do all that in the theory, but in nature, you'd have to have the right stuff to do it.
But that stuff is not real.
That seems to be
as
the
far
case.
as we know.
Yeah.
Now, what would have to happen? Like you would have to have enough power or mass to be able to fold those two things together.
It tends to be weird stuff, like stuff that has a negative pressure or something like that. So stuff that has physical properties that are just bizarre, and that no matter or energy that we know of in the universe has. So that to make the geometry happen.
But it's conceivable in theory that this could exist, even though it doesn't.
It's a debate ultimately. So wormholes are a good example. So that would be quite literally. We talked about the surface of the Earth. So you fly to Australia from LA, and you have to go quite a long way around this edge of the Earth, or you could tunnel straight through and get there quicker, right? So that's a wormhole.
Jamie's got a little graphic up there on the
there it is.
screen for
There's
us.
a wormhole. So you could go all the way around the edge, or you could take the shortcut. So the question is, so you can do that in Einstein's theory. You can write down that geometry, and there it is. So the first question is, can you make it? And as we said, we don't think that stuff exists.
Right.
There's a second set of bits of theoretical work, which are, if you had a wormhole, then what would happen if you tried to travel through it? And what seems to happen is that they become unstable the moment that anything tries to go through. So you get kind of a feedback of stuff going through and through and through and through, and so it collapses. And there's a great book by Kip Thorne, actually. We just mentioned him. He got the Nobel Prize last year for the gravitational waves. And he wrote a brilliant book, I think it's in the 80s, called Black Holes and Time Warps, where he talks about the answer is we don't fully know, but most physicists think that even if they existed, they would be unstable. And as soon as you even tried to transmit information through them, send a bit of light through, then there would be this sort of feedback and they'd collapse. And ultimately, the reason we don't really know absolutely is because you need what's called a quantum theory of gravity, and we don't have one. So we don't have the theoretical tools to be absolutely sure that these things would be unstable or don't exist in nature. But we strongly suspect that they don't. If they did, you could build a time machine. So Stephen Hawking wrote a paper called the Chronology Protection Conjecture. And conjecture is the important word. So the conjecture basically was that the laws of nature will be such that you can't have stable wormholes and you can't build time machines.
And if you sent something through it, it would destabilize it.
Yeah.
And if it didn't destabilize it, how would your physical body deal with the stress of that?
Well, it doesn't have to be that you can build them. That's called the tidal gravitational force. So it's the difference in gravitational pull across your body, which is one of the things that gets you if you fall into a black hole. So before you actually get to the singularity, you can get, it's called spaghettified as a technical word. So you get, and it's just like the moon's, the tidal effects on the Earth, which are quite small, but they still raise tides on the oceans. So that can be if you think about something like a black hole, that can be a massive difference in gravitational pull from your head to your feet, and so it can stretch you out. And so, but you can with wormholes, you can write the geometry down in Einstein's theory such that you could go through. So you don't have to be destroyed or anything weird happen to you.
Would you have to have something protecting you, some force, some sort of a?
No, you just literally you fall through. I mean, so if they would exist, you just go through. You sit in a little spaceship, but you wouldn't. There's nothing inherently in them that says that you would be ripped apart or anything like that. I've been
But for whatever reason, that becomes more interesting because it's in our neighborhood.
Yeah.
Whereas if they find some distant star system and that it might have a planet that's similar to Earth, that doesn't seem as compelling for whatever weird reason.
No, yeah. I mean, I think the planets around Alpha Centauri and Proxima Centauri, which are the closest stars, it seems like there are planets around those now. And I think that was interesting because we could conceive of going there.
Right.
I mean, there was this idea, Stephen Hawking actually and some others before he died had this idea called Breakthrough Starshot, which is the idea to send a little probe out to the Alpha Centauri system. I think in their view, Yuri Milner as well, the entrepreneur wanted to do that. And I think it's something like 100 years travel time or something with our current technology. And they pointed out that we don't do that now. We don't think 100 years in the future. But if you go back when people were building cathedrals, people used to routinely start projects that would take 100 years to bear fruit.
Yeah.
And so we could imagine going there. And that then becomes fascinating, I think, because then you've got a solar system, another solar system that you could go and visit, conceivably.
Conceivably. Yeah, I mean, what kind of speed are we talking and how long would it take to get there?
Well, yeah, I mean, so it is. I think the idea was about 100 years to get there. So it's going 4 light years or so in 100 years, so whatever that turns
So you would
out
have to
be.
essentially do what they did in like the Ridley Scott Alien film and put people into some sort of a
Oh, it'd be a robot
hypersleep?
probe. It wouldn't be a crewed probe.
Wouldn't be possible for a crew,
Well, it is.
but you'd have to freeze them.
Yeah, that's always, when you talk to engineers, you had Elon on, didn't you?
Yes.
Engineers always say, physicists go, well, it's possible in principle, so over to you. You you do it now. There are no laws of physics that tell us we
Right.
can't do it, so we just do it.
Right.
But, it's...
That's a weird relationship
It's
between the
hard.
physicists and the engineers.
Yeah.
Yeah.
But yeah, in principle, you're right. If you can send a little robot spaceship there, you can send a crewed spaceship there.
I'm of the opinion as time goes on and augmented and virtual reality gets better and better that it doesn't really totally make sense unless we're talking about colonizing someplace to send biological life to another planet. And if we can send some probe that doesn't have to worry about the biology being affected by radiation or by the speed of travel or even by food, we can send something out there and almost be there by virtue of goggles, virtual reality goggles, or something else.
Yeah, you hear that. In science, at the moment, space science, we have this debate a lot, actually, because, of course, space probes like Curiosity that's on Mars at the moment, that's really cheap compared to sending people to Mars. And so quite often the scientists who want to find out about the worlds will say, well, we should spend it on robots. We shouldn't spend it on people. I think crewed space exploration is, in some ways, I mean, it's clearly true at the moment that humans can do more than robots, so we can explore the place better.
For now.
Yeah, but I think it has to be, it's about something else. I mean, it's about, and it's not only, it's about living and working off the planet, which I think is quite a persuasive argument, actually. We've already industrialized near-Earth orbit, so it's already a multi-billion-dollar industry, communication satellites and weather satellites, GPS, whatever. We're already up there. And so learning to live and work in space is, I think, a natural extension of our civilization. Plus the fact, if you talk to Elon or Jeff Bezos, they point out that the amount of resources available just slightly above our heads is vast. And so I remember I talked to Jeff Bezos actually once, and he thinks really simply, and he said, for example, in the asteroid belt, there's enough metal, I think, to build a skyscraper. What is it? It's something like 800 stories tall and cover the Earth in it, right? If you want. Now, we don't want to do that. But his point was that the energy from the sun is all up there. The resources are up there. So you could almost imagine trying to zone the Earth residential at some point in the future to protect the planet and do your heavy industry off the planet, for example. And it sounds like science fiction, except that now SpaceX and Blue Origin, those people have got reusable rockets. So suddenly the economics become sensible. So I think expansion is good, and I think we will expand, and I think we will expand outwards because there's not much room left on this planet to expand. So I think we'll do so. But that's a whole different idea. It's not about gathering scientific information. It's about a frontier and all the benefits that come from operating as a civilization on a frontier, which we've sort of lost on the Earth because there is no frontier left. And so I like that idea that Mars, and when you talk about Mars, especially with Elon, he's right that that's the only place you can go. So there is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn. You can't go to Mercury or Venus. So if we want to go somewhere and expand our civilization, it has to be Mars. And everything's there that you need. So, but that's a different thing to saying that you want to find out stuff. You're right. If we just want to find out stuff, then you send robots.
But as far as expanding actual civilization and bringing it to another place, one of the things that freaks me out is people get depressed about living in Seattle. I mean, you're going to live on Mars?
I wouldn't. I agree with you.
Yeah.
It'd be a horrendous thing. It's like it'd be like the Western frontier. It's the frontier when people cross the states.
Yeah,
an incredibly dangerous thing to do.
But when people cross the states, they still got to Wyoming and beautiful places and Colorado and
but it was hard.
Yes,
I wouldn't have wanted to do it.
But once you got there, there's a river and there's trout in the river and the meadows are green and
it's right. I mean, I agree with you, right? I mean, I'm not going to go there till there are vineyards and hotels and things. But however, it is true that there are people who like the challenge. And what is true about Mars, it's interesting actually because we know something about the history of Mars now, quite a lot about the history of Mars, and it's certainly clear that there was water. Almost certainly oceans, rivers. So, and that water is almost certainly still there. So I would say certainly still there.
Well, they have found large quantities of ice now, right?
Yeah, so there's certainly ice. There may even be pockets of liquid water below the surface somewhere. So couple that with all the minerals and the resources that we know are there, and you have everything you need. So that's the thing about Mars. It's quite nice relative to everywhere else other than the Earth. You can't go to Venus, right? You just melt. It's, 400 and something degrees and 90 atmospheric pressure.
Yeah.
So Mars is quite nice. But I wouldn't go there. I agree with you.
What's the gravity of Mars in relationship to the Earth?
It's about a third, I think.
Third,
right? Yeah, something like that.
So it would still have a significant weakening effect. Like if you went to Mars and then somehow or another in the future they were able to get back to Earth, your body would have a real problem with that, right?
It would, but there is still gravity. Maybe it's a bit more than a third. I can't quite remember, but it's something like that. But yeah, so there's still gravity. Right. So there's gravity. There's some protection from you'd probably want to live in the caves actually or something like that because there's no magnetic field there, so it's quite a high radiation environment, but not too bad. It's further from the sun than we are. It's not too. There are places on Mars. There's a very deep crater called Hellas, which is a big impact basin, and at the bottom it's so deep you could fit Everest in it. So you put Mount Everest in there, the summit of Everest wouldn't reach the rim of the crater. So it's something like, I don't know what it is, 7 miles deep or something, 6 miles deep. So you could go there, and at the bottom, the atmospheric pressure is so high that you could just about have liquid water occasionally on the floor of that crater. And it's quite warm sometimes. It can be 20 degrees.
Really?
Yeah, there, Celsius.
Wow. So better than Minnesota right now.
Exactly.
Minnesota's experiencing a serious cold front.
That's right, yeah. So it can be warmer than Minnesota. And so there are places where it's not horrendous on Mars. So the Martian is kind of realistic in that sense.
One of the biggest mind-blowing moments, I think, of my limited comprehension of what it means to be a living being was when I found out that carbon and all the stuff that makes us has to come out of a dying star.
Yeah.
That alone, that there's this very strange cycle of these enormous fireballs that forge the material that makes Brian Cox.
Yeah.
What? That one alone, that there is some strange loop of biological life that comes from stars, which is the most elemental thing that we can observe. We see these things in the sky. We see the sun in the sky. It's this all-powerful ball of fire. Yeah. And that is where the building blocks for a person come from?
I know. And they will be from the carbon atoms in our body. That you're right. They all got made in stars because there's none of it at the Big Bang. There's only hydrogen and helium, tiny bit of lithium to be precise, but nothing else. And so it was all made in stars. And it's probably from different stars. You know, the atoms in your body, they're not all from one star that cooked it and then died. There'll be a mixture of stuff from many stars in your body now. And I agree with you. What more do you want? You know, when I see people who go, I want more than that. I want more. You know, there must be more to it. What do you mean? We were the ingredients in our body.
I think I think a lot of people aren't aware of all the information, right? And then I think on top of it, for some people, it's so overwhelming.
Yeah.
This concept of 13.8 billion years of everything to get to this point that we're at right now. It's so overwhelming that they want to simplify it.
Yeah.
They want to put it into some sort of a fable structure, something where it's something that's very common and similar and familiar.
Yeah, I agree, but I think that's the journey that we go on. The real treasure, I think, is in that journey of trying to face the incomprehensible.
Yes,
it's in that realization that it's almost impossible to believe that we exist. Right?
yes, right.
But that's a wonderful thing.
Yeah,
and I think that's what I think you miss out. I think if you decide to simplify it because you don't want to face that, you don't want to face the infinity that's out there in front of us, and you don't want to face those stories, as you said, that you look at your finger and its ingredients was cooked in multiple stars over billions of years. That's to me a joyous and powerful thing to think about.
yes.
And I think you're missing out if you don't want to face that.
Well, I think the distribution of information has changed so radically over the last couple hundred years, and particularly over the last 20, that you're seeing these trends now where more people are inclined to abandon a lot of even if you remain religious or you keep a thought or a belief in a higher power, people are more inclined to entertain these concepts of science and to take in the understanding of what has been observed and documented and written about among scholars and academics. And there's more people accepting that. If you look at the number of agnostic people now as opposed to 20, 30 years ago, it's rising. It's changing. And I think there's also, because of you and because of Neil deGrasse Tyson and Sean Carroll and all these other people that are public intellectuals that are discussing this kind of stuff, people like myself have a far greater understanding of this than I think people did 30, 40 years ago.
Yeah.
And that trend is continuing, I think, in a very good direction.
Yeah. I mean, what we should say is that science, we don't know all the answers. So we don't know where the laws of nature came from. We don't know why the universe began in the way that it did, if indeed it had a beginning. So we don't know why the Big Bang was very, very highly ordered, which is ultimately, as Sean Carroll, actually, you mentioned him, often points out, and he's right, that the whole difference, the only difference between the past and the future, the so-called arrow of time, is that in the past the universe was really ordered, and it's getting more disordered, and that necessary state of order at the start of the universe, which is really the reason that we exist. That's the reason, because the universe began in a particular form. We don't know why that was, so we will probably find out at some point, and it'll be something to do with the laws of nature. But so I'm always careful. I don't want to. Science can sometimes sound arrogant, right? It can sometimes sound like it's the discipline of saying to people, "Well, you're not right."
Yes, yes.
And it's not the discipline of saying you're not right. It's saying this is what we found out,
Yeah.
I like to say that it provides a framework within which, if you want to philosophize or you want to do theology or you want to ask these deep questions about why we're here, you have to operate within that framework because it's just an observational framework.
Yes.
So everything we've said is stuff we've discovered. It's not stuff that someone made up, right? We understand nuclear physics. We can build nuclear reactors, for example. So we understand the physics of stars. So we understand that the stars built the carbon and oxygen, and we know how they did it. We can see it because, as I said before, if you look far out into the universe, you're looking way back in time. And as you look back in time, you see less carbon and less oxygen. So we have a direct observation that in the earliest universe, there wasn't any because we can see it. And now we see that there is some and we know how it was made. So I think it's important to be humble when you're talking about science. And you're not saying this is the way that it is. I mean, you are in a sense, but it's not able to answer ultimate questions at the moment. It's not able to answer even whether the universe had a beginning or not. We don't even know that. And I gave a talk to, I was asked to give a talk to some bishops in the UK about cosmology. And I said, yeah, that'll be great fun. And so I went and gave them this talk. And at the end, I said, I've got some questions. So if the universe is eternal, and it might not have had a beginning. If it's eternal, what place is there for a creator? That's a good question.
Right.
They didn't have an answer, of course, right?
An eternal creator.
But I think that it might be eternal, and we might discover that. So we don't know at the moment, but we might. So I think my point is that these other human desires, it's very natural to religion's a natural thing, right? People, you see it all across the world in all different cultures. But I think that in the 21st century, religion needs to operate within that framework. If it's going to operate, there are still great mysteries, and it is appropriate to think about what it means to be human. And I've given you my view of what it means, but I don't think the problem comes when your theology or your philosophy forces you to deny some facts, some measurement. These things are measurements. We're not saying, it's not my opinion the universe is 13.8 billion years old. We measured it. It's like having an opinion between the distance from LA to New York. You can't have an opinion on that.
Right.
We know what it is. And it's the same,
Right.
It's like, these things, that people say the earth's flat or whatever. So it isn't, and we've measured it. So it's just stop it. But that doesn't mean you can't be spiritual and you can't be religious, I would say. And it doesn't mean you can't believe in God or gods. That's not ruled out.